Welcome to this session. In this session, we are going to talk about the flyback converter. The basic operation of the flyback converter. This is very similar to the back boost converter. So the operation of the flyback converter is very similar to the back boost. You are going to see that we basically have the back boost converter over here with the introduction of our transformer. So if we go to the modeling of the transformer, this is what we have with the arrow pointing down. So very brief. So we have the switch. So this is our MOSFET or our BJTs which we are using. That is our input voltage. Then we have the magnetizing inductance. So this is the inductance we really need to design to make sure that the flux in the core always retains to its original value. And then we have the windings of the transformer. So these are the ideal windings, the primary winding and then the secondary winding of the transformer. We then have our diode. The voltage across the diode is VD, and we have our capacitor and we have our load. One thing to note about this transformer winding is the dotted. So if you look on the primary side, we have the dotted terminal up, and if you look on the secondary side, we have the dotted terminal down. So what did we say about the transformer model? When current enters into the primary dotted terminal, we expect current to leave the secondary dotted terminal. So that is a positive direction of current in I2 on the secondary side. In addition, the voltage polarity on the primary side is positive at the dotted terminal, and on the secondary side is also positive at the dotted terminal. So everything is set up right. With this one, we can use the relationship between the voltage, the primary side voltage, the secondary side voltage, and then the turns ratio, which is N1 and N2. The same thing applies to the current. So now let's take a close look at the operation of this flyback converter. When we close the switch, what do you think is going to happen? As a brief explanation before we take a look at the analysis or the equivalent circuit for that, when this switch is closed, basically you are going to be flowing current through the magnetizing inductor, and also you are going to try to flow current through the primary winding. Flowing current through the primary winding in this direction is going to cause current to flow into the secondary winding. So that's the direction of I2 as we have over here. This direction of I2 implies that current is flowing through the diode in this fashion. Current, we know, cannot flow through the diode in that, which means the diode is going to be reverse bias. The secondary side is going to be open circuit, and therefore no current is going to be flowing in the secondary winding. If there is no current flowing in the secondary winding, then what it implies is that there is not going to be any current flowing in the primary winding, and this is a primary ideal winding, although we are going to have current flowing through the magnetizing inductor. Okay, so let's take a very quick look at the equivalent circuit when we have the switch closed. So this is what we have. So the diode is going to be open circuit. No current is going to be flowing in the secondary side, so that is going to be 0. So I2 here is going to be 0. Since no current is flowing, it means that there is no current flowing through the primary ideal winding, or the current is going to flow through the magnetizing inductance. We've seen this a couple of times. The voltage across the magnetizing inductance is clearly equal to what? The input voltage, which is Vs. So if we use the inductor law, it tells us that the current in ILM is going to continue to increase until we open the switch. So this is what we are going to have. We are going to have the current flowing in the magnetizing inductors increasing linearly when the switch is closed. When the switch opens, the current is going to start dropping. But the period from when the switch is closed till the switch opens, that is what? That is our dt. We are going to have a change in that particular current, which is going to be flowing through what? Our magnetizing in our magnetizing coil. That change we are calling change in ILM. So when we use the analysis over here, we can then derive that change, the expression for that change. So the change in the current which is flowing through our magnetizing inductance when the switch is closed is given by that expression. The input voltage multiplied by what? The duty ratio times the period, all divided by Lm. All divided by Lm. Now, let's look at what is happening across the diode. So very briefly, now that the diode is open circuit, we know there's going to be a voltage across the diode. We want to be able to calculate this voltage and make sure that the diode will be able to withstand this voltage. How do you calculate the voltage across the diode? Okay, so on this side, you see it's positive on that side and negative. On this side, so VD is basically the voltage at this terminal minus the voltage at this terminal. The voltage at this terminal, if you look at the polarity of V2, we have the negative polarity over here. So it's going to be negative V2 minus the voltage at this terminal. And what's the voltage over here? The voltage over there is VO. So to calculate the voltage across a diode when it is reverse bias, to make sure that our diode will be able to withstand that during operation, this is the expression that we need. So that voltage is going to be negative V2 minus VO. How do you calculate negative V2? We know when you go up, we know the voltage across the primary side has been established. Why? Because the input voltage is across the magnetizing inductance, and that same voltage is across the primary winding. Therefore, the voltage across the primary side is established, is known. Since that voltage is established, we can use that with the turns ratio to find the voltage across the secondary winding of the transformer. So that's what we are doing. So over here, the voltage across the secondary winding of the transformer is giving us what? V1 N2 over N1. What is V1? V1 is the same as this input voltage, which is the voltage across the magnetizing inductance. So if we substitute V2, which is equal to that, so we have negative V2. So the negative of this expression minus VO is giving us that. This is less than 0. The magnitude of this is less than 0. And this is what is reverse bias in the diode. And this is the magnitude of the voltage which is going to be across the diode anytime the diode is off. And we have to make sure that the diode will be able to withstand this voltage. In addition, we know that the current in the secondary winding is going to be 0 because the diode is reverse biased based on the direction of the current. And since the current is 0 in the secondary winding, then we expect the primary winding current also to be 0. So as a brief overview to end this session, and then we are going to go to another video to look at the situation when the switch is open. We know that when the switch closes for the flyback converter, current is going to increase linearly in Lm. And we know that no current is going to flow in the ideal winding of the transformer. The implication of this, if you have an actual transformer in the field, what it means is that current is increasing linearly in the physical primary winding of the transformer, whereas no current exists in the secondary winding. So in the physical primary winding, current is going to be increasing linearly, and when you go to the secondary winding, there is going to be no existence of current because the diode is going to be reverse biased. We are going to end this session over here and start a new session later, where we are going to take a look at the analysis of the flyback converter when the switch is open. Thank you.